So you might have been thinking to yourself, what initiates melting? I keep saying if you have a rock and you increase the temperature, you'll get this, but why does the temperature increase, right? And there's right, three reasons that a rock could melt. One of them is temperature increase, but rock can melt other ways as well. So we're going to talk about decompression melting, flux melting, and heat transfer. First up, decompression melting. So coming back to our diagram here, let's say that we're starting at location C, right? And let's say that our rock is not water saturated, it's anhydrous. So at this point, it's going to be a solid rock if it's at C. Right? Now, decompression melting means that that rock is decompressed, right? It rises up in depth so that the pressure is reduced. And as pressure is reduced, right, that pressure kind of lets go of those atoms. Those atoms can start to spread out a little bit more. And as atoms spread out a little bit more, they can turn into a liquid, right? So that's decompression melting, right? When something decreases in pressure and melts, and this is when temperature can stay the same, right? Temperature does not have to increase here. Temperature can stay the same, but the rock will still melt because of the decrease in pressure. We call this adiabatic melting when the temperature doesn't change. So what kind of geologic environments do you think are the most conducive to decompression melting? Where on Earth are rocks going to be rising towards the surface? Well, there's lots of places. Mantle plumes, right? We know that anywhere there's a plume of magma, a concentration in the magma in the mantle, that liquid is lower density than the rock around it, so it's going to rise up. Could create decompression melting, make that mantle plume bigger and bigger and bigger as it rises towards the surface. This also happens at a continental rift, right, where the land is being pulled apart. The lithosphere is getting skinnier and skinnier and skinnier, and the asthenosphere is rising up. And if this continues to happen and that continental rift actually turns into an ocean and a mid-ocean ridge in the middle, there's tons of decompression at mid-ocean ridges, right? That's where a lot of the magma that reaches Earth's surface is coming from. So decompression melting at divergent plate boundaries is by far the most important on the planet. Yes, decompression melting happens at mantle plumes, hotspots, things like that, but divergent plate boundaries are by far the most common. And when partial melting occurs, the mantle peridotite produces a liquid of basaltic composition, which is one of the reasons that our ocean floors are made of basalt, right? But at this shallow depth, the basaltic liquids contain a slightly higher silica content than they would for decompression that happens deeper, such as at hotspots, right? So 52% silica at mid-ocean ridges, whereas there's less than 50% silica at hotspots.